Hello guys, welcome to Coding. In this video, we are going to see the Leetcode problem number 1926 nearest exit from n times in maze. Let's get into the problem. So the problem statement is you are given an M into n m cross n matrix maze with empty cells and walls. You are also given entrance of maze where entrance is entrance row and entrance column. So which denotes the row and column of the cell you are initially standing at. So yeah, there's a M cross N matrix maze and there is a empty cells is represented as uh, full stop and the walls are represented as positive sign. So in one step you can move one cell up, down, left or right. You cannot step into a cell with a wall and you cannot step outside the maze. So the directions are given and they have given that you cannot step into a wall and you cannot step outside the maze. So your goal is to find the nearest exit from the entrance. And an exit is defined as an empty cell that is border of the maze. The entrance does not count as exit. So return the number of steps in the shortest path from entrance to nearest exit or -1 if no such path exists. So this is the problem. So now let's get into the problem definition. Yeah, let's go to the paint. So before solving any problem, we need to define the problem clearly. So the input of the problem is the maze of m cross n of m cross n and position entrance of size 2, which is denoting the x and y coordinates of the maze. So output is nothing but minimum number of steps to reach min steps to reach exit. So these are about the all about the input and output. So what is an exit? So exit is nothing but a cell in which is border of the maze, which is nearest to the border of the maze. So let's see. So anything defined as empty cell that is border of the maze. Yeah. So which is border of the maze. That is the cell should be a empty cell and not a wall. So this is all about the and also the given condition is exit is entrance is not counted as exit. Entrance not equal to exit. This is the first point. This is the second point. And the third point is the directions given are up, down, left, and right. These are the directions. So if you're unable to reach the exit from entrance, we need to return -1. So when we can't reach exit, return -1. And they have given that walls are represented as plus sign and empty cells are represented as full stop. So yeah, these are all about our problem definition. So Let's get on to approach of this problem. So I'll edit this. So next step is the approach. So how to approach this problem? So you can clearly see that we have a starting question in the mess. So they have asked for minimum number of steps, right? So that is shortest path. So there should be minimum number of steps. So when we get these type of questions, we can try to find the pattern, and you can clearly see that we can use a queue to find the shortest path. So queue can be used in application in graph problems where minimum path is required. So the queue can be used in these type of questions. So how can we utilize the queue in this problem? So initially what we are going to do is add the um, what to say. So we need to add the cells which are add the cells. Sorry, first we need to create a queue. So we'll create a queue. So we'll add the if this is the start, we need to add the uh, cells that are empty, that can be reachable from the start. So we'll go to move to all directions. So we'll move to all directions and start to traverse from those directions. So we can also use DFS approach, but DFS approach is very efficient than the DFS, because in DFS you'll go to unwanted paths. So even if we get the answer at 4, sometimes you may go to like depth of 100. So if the answer lies in the depth of 4, but there is a possibility that you may even go to depth of 100 or long. So DFS should not be considered for this problem, but even the DFS gives us answer. So but it increases time. So it may lead to time limit exceeded time complexity. I mean error. So how to avoid this? So you can use BFS. So BFS helps to go level by level. So if answer is found in any level, we'll stop the iteration and return the answer. So this is the advantage of using the queue. So initially we'll add the empty cells of distance 1. So all the empty cells of distance 1 will be added, and all the empty cells of distance 2 will be added, and so on till the desired answer, that is exit is reached. So if exit is not reached, so this may lead to exit or no remaining cells. So in these cases maybe we'll have 4 directions. So for each cell we have 4 directions, right? So for each cell we'll add the neighbor cell which are empty cells. So this is the first step, and when we find an exit, we'll return the level. So we'll return the level, that is the path steps taken. So or else we'll return the -1. So no exit is possible from the entrance. So this is the approach we are going to use. So what are the steps in the approach? So yeah, I'm going to say the steps involved in our approach. So initially we'll create a queue, and the second step is you'll add the reachable empty cells. Empty cells from entrance. So the third step is to find the number of positions in the queue and traverse over each element, that is each position, and add the uh, irreachable empty cells from the nodes. So when we consider, initially we'll have the we may or may not have positions in the queue. So we'll add up the nearest positions, and I mean the empty cells on this reachable entry, and we'll take those empty cells and again add the other empty cells. So we'll go level by level and check if it is an empty. If check if exit, we'll return level plus one, or else we'll continue adding empty cells. So this is the approach, and while adding each reachable while adding each empty cell, we are going to change the value from full stop to this dot to plus symbol. So why we are doing this? So we don't want to add the same nodes again and again. So what we are doing is, when we are adding a node to the queue, that is when we are adding a position to the queue, we'll change the corresponding cell value from full stop to dot. So this is the extra point we are going to have from this approach. So yeah, this is all about our approach. So first step is create a queue, second step is add reachable empty cells from entrance, and third step is we'll go level by level and check and pop elements. So we'll go level by level and take the empty cells, and we'll check for each empty cells in current level. For empty cells, we'll check whether it is exit or not. If it's exit, we'll return the level plus one. So this is level plus one, or else we'll continue adding empty cells, that is reachable. So that's all about our approach. We are not going to do any extra things out of this approach, so we are going to use the same approach in this coding. So let's get on to coding session. There you'll get the clear idea of how to follow all these steps. So yeah, initially we'll create a queue of int array to denote the position. So let's call queue as position. So we have a direction two-dimensional array, new direction of 1 comma 0, which yeah, I'll discuss why we are using this array. 0 comma 1 and minus 1 comma 0 and 0 comma minus 1. So this is the direction array. So why we are going to use this? So in order to when we are currently in the current cell, so how to go up. So in order to go up, we need to reduce the x coordinate. So we need to reduce the row. So we are using the denoting the row as first index and column as second index. So when we add up this to our current cell, we'll go down. This will take us to right. This will take us to up, and this to left. So yeah, you'll get clear idea of what this in the way we use this direction array. So yeah, initially we get the first step, which is queue creation. Create a queue. So step 2 is add reachable nodes from entrance. So we'll call a helper function add reachable nodes of let's say maze and entrance. So before that, we'll since we are starting from this current cell, we are making the entrance, this entrance entry as already visited. So we'll make it to wall. Entrance of 1 equal to plus. So we have reached entrance. So we are marking entrance as wall. Why we are doing this? So that when we go to next level, we don't return to the same previous level. So yeah, we are going to call a helper function mains entrance and the positions. So we have the initially have the steps step count as 1. Why we are having 1? Because from the entrance we are going to one step. So we have already taken the one step. So for each time we have increment the step count. This is nothing but level. So we have declared as a step count. So we are going to iterate over queue. So while positions dot is not empty, actually we find the size of current level. So we'll iterate over each size, each position. So for each position, what we do is if it is exit. So if we check whether the given current position is exit or not, we'll use a helper function. So we'll pass the maze and current position. So before that, we'll fetch the current position. So current position is nothing but positions dot hold. So we'll pass the current position to the exit function. So if it is exit, we'll return the step count, or else we'll add the reachable nodes. That is, we'll pass the maze, entrance, and positions. And finally, we'll increment the step count. So when we have no possibility of reaching the entrance, I mean the exit, we'll return the -1. So we'll write the helper function, that is add reachable nodes and the exit function. So private void add reachable nodes of, we'll get the maze, which is two-dimensional character array, and entrance, which is the current position, and queue of position, which is position. So what we do is add the reachable nodes. So what we are going here is the helper function is add the reachable nodes from positions. So reachable empty cells. So here to add reachable empty cells from entrance. So position. So for each direction in direction array, we are going to have two coordinates, that is x is nothing but position of 0 plus direction of 0, and y is nothing but position of 1 plus direction of 1. So if we meet the boundary condition, so which is if x is equal to minus 1, is these boundary conditions are nothing but when we have the current position, that is x comma y coordinate lies outside the maze. So if y equal to minus 1 or x equal to maze dot length or y is equal to maze of 0 dot length. So these are boundary condition for checking whether the position xy is out of maze or not, and the final condition is going to be whether the current cell is a wall or not. If it is a wall, we'll don't add the cell, right? So we'll continue. Or else we'll add the current position into Q. So before and add while we add, we also have an extra point that we'll make the position current position xy as a wall. So this is all about a helper function, and we'll find write the helper function for exit. Yes, exit, and we'll get the parameters that is maze and position. So what the helper function does is it will check whether the position is the exit of the maze or not. So what is the exit in this problem? So exit is nothing but the border of the maze. So borders are nothing but when we are at first row, first column, last row, and last column. So these are the borders, right? So we are going to check for every borders. So if row is nothing but position of 0. So if position of 0 is 0 or first row, and if it is first column, the column should be 0, or if position of 0 is equal to maze dot length minus 1, or position of 1 equal to maze of 0 dot length minus 1, will return true or else false. So we'll have just have a condition operator. So we'll directly return it. So we'll directly return the value. So this will reduce the size of the code. So that's all about our coding. So what we have done, so initially we created the queue, and step 2 is we are adding the reachable nodes from the entrance, reachable empty cells from the entrance, and we are having the step count as 1, since we have moved one step from entrance to the current nodes at the current cells at the positions. So we are going to iterate over the queue, and for each time we are finding the size of the cells, so at the current level, and we are adding we are polling this position, and we are checking if it is empty, that is if it is an exit. So if it is an exit, we'll return the step count, or else we'll add the reachable nodes, and we are incrementing the step count, and finally we'll return minus 1 if it is not possible to reach the exit. So in the add reachable, so we'll call this as reachable empty cells. So add reachable empty cells. So yeah, for each direction we are going to have the x and y coordinates, and we're checking the boundary conditions, and if the boundary condition is not met, it will help us know that the current cell is an empty cell. So we'll add the cell to the queue and also make the current cell as a wall. So its exit will help us to find whether the given position is an exit of the maze or not. So we will check whether the position is the boundary condition. So yeah, we'll check this. Getting wrong answer. So let's see what is mistake here. So this is the test case, and we have marked the current position as wall, and we are adding the reachable empty cells. So maze, sentence, and position are passed. So for each direction, we'll check whether x and y are out of bounds, and also whether it is plus or not. It should work fine, right? So we'll be going in the second test case, we will be going right. So this should be the answer. 2 is the answer, but we are getting -1. So we'll check whether we are adding these positions properly in the first case. So we'll pin the maze positions. Yeah, it's getting added properly. What is the mistake here? So initially we get the size, and for each position we are checking if it is exit. So if that is it is not an exit, we'll add the reachable empty cells. So again we'll move to right. So this will be added to the queue. So we'll check whether the rightmost cell is added or not. So we'll check the we'll print the step count. Yeah. So I think we are not adding the empty cells properly. So we need to check the base case. So sorry. This should be the position. We have used entrance here. This will be the current position. So this position should be passed into the reachable cells. So let's check this out. Let's submit it up. Accepted. And the time complexity of this approach is nothing but order of maze dot length into maze of 0 dot length. So this is because we'll iterate over the each cell at least one time. So this is the worst case. It will be measured into 4 since we move to every 4 direction, but this is the constant, so we'll avoid this. And the space complexity nothing but log maze dot length into maze of 0 dot length. So this is because we'll maximum add up every cell into the cube. So this is the space complexity, and the approach for this problem is nothing but BFS. So that's all about this video, guys. Thanks for watching this, and have a great time.